So how does science change in the Cold War? There's two ways we might approach that. First, in thinking about scale, and then thinking in terms of its organization and direction. In terms of scale, where we start, in 1938, the total U.S. budget for military R&D was $23 million. In 1945, in contrast, the OSRD spent more than $100 million, and the Army and Navy together spent $700 million, and the Manhattan Project itself spent $800 million. Post-war spending was 30 times pre-war levels and up to 90% of all federal R&D. This leads us to ask, what is the nature of post-war science? This has gone under the name of big science, and it has four major features. First, big science is goal-oriented. No huge sum of money could be dedicated without a mission and without outcomes that could be articulated and predicted. So the very success of the Manhattan Project as an organized, mission-oriented project encouraged the view that it was a model for other scientific and technological projects. It would be a model in the post-war period for how to do science. Second, the expense of big science leads to a concentration of resources, resulting in turn in decreased number of leading research centers based around special facilities. In post-war particle physics, for instance, the discoveries and prizes have generally gone to teams working with the highest energies, highest funds, and most number of people. So Europe and Japan have struggled to compete with the facilities available in the United States. As numbers of staff have increased, and as the instrumentation has become more complex, so too has there been an increased need for specialized expertise for the work of such experts to be coordinated and controlled in an efficient manner. Therefore, third, big science was marked by a fine division of labor, hierarchically organized into groups, with group and higher-level managers. There was a concomitant division within technical and scientific staff into specializations. So a particle accelerator laboratory such as at Brookhaven or CERN had distinct teams of theoreticians, instrument builders, experimenters, and so on. This trend toward fine division of labor could also be enforced by the trend toward militarization, since both favored the compartmentalization of work and knowledge, although for different reasons. Fourth and last, big science was marked by a high political significance, and this was attached to mission-oriented, expensive projects, although the proposed contribution varied. So, one mission might be toward national health, another toward military power, another toward industrial potential, or to national prestige. Along with political significance came media management. In the Cold War, political significance was, unsurprisingly, the extent to which the scientific or technological achievement could be presented as a triumph of a form of society, namely American society. The most extraordinary denunciation of this kind of big science came, in fact, from the Commander-in-Chief, the President of the United States, Dwight Eisenhower, in his farewell address to the nation on the 17th of January, 1961. The mobilization necessary to meet a hostile ideology, global in scope, atheistic in character, ruthless in purpose, and insidious in method, he said, had led to a permanent rearmament that was becoming deeply rooted, institutionalized power. So he warned the American people, quote, "We must guard against the acquisition of unwarranted influence, whether sought or unsought by this entity which he famously named the military-industrial complex." Akin to and largely responsible for this danger was the technical revolution during recent decades, he said, which emerged from a second threat, the corruption of democracy by technocratic influence. He said, "In this revolution, research has become central. It also becomes more formalized, complex, and costly. A steadily increasing share is conducted by or at the direction of the federal government." He added, "Today, the solitary inventor tinkering in his shop has been overwhelmed by the task forces of scientists in laboratories and testing fields. In the same fashion, the free university, historically the fountainhead of free ideas and scientific discovery, has experienced a revolution in the conduct of research. Partly because of the huge costs involved, a government contract becomes virtually a substitute for intellectual curiosity. For every old blackboard, there are now hundreds of new electronic computers. The prospect of domination of the nation's scholars by federal government, project allocations, and the power of money is ever present and is gravely to be regarded." So, he warned, science itself is threatened by bigness. Science itself is threatened by the money coming from the government. Yet, In holding scientific research and discovery in respect, as we should, he said, we must also be alert to the equal and opposite danger that public policy itself could become the captive of a scientific technological elite. Eisenhower said it is the task of statesmanship to mold, to balance, and to integrate these and other forces, new and old, within the principles of our democratic system, ever aiming toward the supreme goals of our free society. So this led to a question. Was science corrupted? Historians have given two answers to this kind of question. They note that the United States defense establishment was indeed the major patron of the sciences, especially the physical sciences. Private foundations, previously the pacesetters for American research, could no longer offer comparable grants to those available from the Atomic Energy Commission and the Department of Defense, and so these foundations withdrew from the natural sciences. Throughout the 1950s, the only significant sources of funds for academic physical research in the United States were the Department of Defense and Atomic Energy Commission, whose missions were de facto predominantly military. These two bodies each provided roughly half of all the funds of unclassified basic research in university physics departments, and they provided pretty much all of the research funds for classified physics research. Second, historians note that funding source made a difference in the direction that science moved. There was a mutual orientation in this period of interest between the patrons in the federal government and the physical scientists. The problems chosen were those of military interest, secrecy, the military necessity of classified information, and so on were encouraged and enforced by this form of funding. Under military patronage, the social organization of science was a distinctly large-scale, hierarchical social framework. In the words of an academic administrator speaking in 1953, there was a time when scientific investigation was largely a matter of individual enterprise. But the war taught scientists to work together in groups. They learned to think in terms of a common project. They were impressed by the progress being made through unified action. A notable degree of this spirit has been transferred into the life of our larger universities. The scale of research and the complexity of its technique have grown beyond anything imagined a few decades ago. It was the war that contributed principally to the major revolution in methods and spirit of laboratory investigations. With this change, with a massive investment in scientific research, doing experiments was an industrial and military project. So who is the experimenter and whose activities have we been discussing? Rarely, if ever, is he a single individual. The experimenter may be the leader of a group of younger scientists working under his direction. He may be the organizer of a group of colleagues taking the main responsibility for pushing the work through to successful completion. He may be a group banded together to carry out the work with no clear internal hierarchy. He may be a collection of individuals or subgroups brought together by a common interest, perhaps even an amalgamation of previous competitors whose similar proposals have been merged by a higher authority. So the experimenter then is not one person, but a composite. He may be 3, but more likely 5 or 8, but possibly as many as 10 or 20 or more. He may be spread around geographically, though more often than not, all of him will be at 1 or 2 institutions. He may be ephemeral, with a shifting and open-ended membership whose limits are hard to determine. He is not a person, he is a social phenomenon, varied in form and impossible to define precisely. One thing is sure for certain. He is not a person. He is not the traditional image of a cloistered scientist working in isolation at his laboratory bench. To think about the scale and military nature of the work, consider, if you will, the physicist Donald Glaser, who won a Nobel Prize for Physics for inventing the bubble chamber. The chamber was filled with liquid hydrogen. Making liquid hydrogen was a difficult and new thing. One reason that it is hard is that making liquid hydrogen involves cooling it to negative 246 degrees centigrade. And of course, hydrogen is highly explosive. Incidentally, the technologies for doing these experiments were cast off from a military application, that is, the design of the test of the first hydrogen bomb. So why hydrogen? Why use this? Well, if subatomic particles moving at very, very high speeds collide with atoms of the liquid hydrogen, they will produce a shower of new particles, which will then produce a cascade of other collisions and collide with other particles of the hydrogen. Where these particles move through the liquid hydrogen, they will heat that hydrogen up and it will boil, leaving tracks of bubbles of now gaseous hydrogen. But you need to get particles going really, really fast before the collision. For that, you need a particle collider. And the US built several at the expense of the taxpayer, including the Stanford Linear Accelerator, which Glaser worked. This instrument, the collider plus the detector, were no tabletop experiment. They involved digging miles of ditches, large construction, trench digging, and cast-off military equipment. But once you had a picture of the particle tracks, it had to be deciphered and interpreted. For that, women who knew math and physics were necessary. These women were tasked with looking at pictures produced by the bubble chamber. They were tasked with classifying the lines of the tracks, identifying individual particles, and calculating their trajectories. After all this work, one woman might find a track that seemed to show a particle that behaved in a way that was not previously seen before. To do that, she had to know how all the previously known particles behaved. If there seemed to be a new particle that she had discovered, then someone like Donald Glaser would take credit for the discovery and be a candidate for the Nobel Prize. This male physicist would take credit even though he might not have designed the detector, not designed the accelerator, or have built either. And he would receive credit even if someone else, that is, one of the women who was working at the scanning machines, had first identified the particle in question as doing something as never seen before.